Okay, I think you can see Pablo and for the and the rest of the organizers. It's a nice opportunity, and well, it's a very nice to be in here. Well, let me. I am a scientist, right? I'm not just an entrepreneur by just very recently, but I am a scientist. I'm still be, and I will be forever. So, but I incidentally I co-founded this company, and we are in this adventure. Still, I'm a scientist. As I said before, I work at I have a part-time job at the BSc at my research center, and a full-time job at the company as CTO CSO since 2018. But in any case, I am CTO CSO. I am more related to the scientific and technology stuff in the company. So my life didn't, well, it changed, but my duties didn't change that much because still I am involved with the technical issues. But I had to learn plenty of things related to the company. So in the company there is a CEO also.
Mariano, sorry for interrupting. You are sharing. I don't know whether you have two screens. We see.
No. Yes, it's fine. It's fine. It's okay. It's okay. It's on purpose.
Okay.
Okay. So I am there is another guy which is the CEO, and we're at this moment we are 8 people. So the CEO is mostly in charge of the business. And now, well, this is the typical that you are seeing now, I guess. This is the typical presentation that you give to investors. What we are doing what we are doing now is the fundraising. So this is the typical one I give to investors. So when Pablo told me about giving this talk, I said, okay, I can do something like this, but a bit increased with some other more technical stuff. But I don't want to, then afterwards I said, no, I don't want to submit people to these things which can be a bit annoying. So I did differently. So what I did, I have prepared another presentation, which is the typical one that I gave. It's starting now, I assume. So this is the good one, not the other one. Just I wanted to show the other one just to start showing you the main differences that happen to your life when you are doing these sort of things. That you have to change a bit your mindset, or a lot, depending on the position that you take, but a bit or a lot your mindset, and be prepared to give presentations that I will see these off the record. If it would be great if you stop the recording now, but you have to learn and be prepared to give boring presentations. I hope this will not be one of the boring ones. Because the idea is that the presentation I will give is the kind of presentation that I give to show what the company does in more technical arenas. So it is everywhere is transpired the idea of the company, but there are some technical things. So the important thing here is that this is given to people to show the history of the company, where it starts, at which point we are, and what are the things that we're doing, and especially related to the technical points and why we created the company, let's say. So this is the good presentation, and this is the idea of giving this presentation. So if you come to Barcelona, there are plenty of churches and chapels and large cathedrals in Barcelona, of course. And there is here, you can see Sagrada Familia, the cathedral. But there is one, Santa Maria del Mar, but there is one which is not that much well known, which is this one. But it has started to be well known because within this chapel you have this computer. This computer is Mare Nostrum 4. So if you think about a pyramid, this is the lower layer of the pyramid, the computer. So we have this very large computer. It is one of the largest in Europe. This is Mare Nostrum 4. It is 11 petaflops. We have already, we are right now finishing the procurement for Mare Nostrum 5, which is going to be 10 times larger, a pre-exascale computer. It's not going to be in the chapel. We are going to maintain the chapel for smaller computers like this one, but they are building another building just by the chapel in which the larger computer will be set. So this computer is hosted by Barcelona Supercomputing Center. At the higher level, you have this Barcelona Supercomputing Center. So the computer was first, and then it came the center. It was a kind of a joint negotiation, but then it came the center. The center is in charge of hosting the computer, do the maintenance of the computer. We are kind of between 500 and 600 researchers now. It's a Spanish public research center located in Barcelona. Well, this is the Sagrada Familia. It is not our chapel, but well, if we keep on growing, I don't know, Mare Nostrum 7 where it's going to be. Why not Sagrada Familia, I would say. So the center was created in 2005, and as I said, is a research center. It is not just a place for hosting the computer. And within this center, there is our team, the ALYA development team. So right now, we are kind of about a bit less than 10% of the researchers of PSC are in our team. There are different profiles: mathematicians, physicists, engineers, programmers, and senior and PhD students. It was born at the same time at BSc in 2005. It's nice that we started by being 2, and right now we are kind of almost 50. So at the top of the pyramid is the company LM. LM is a spin-off company of BSc, and the idea is to make much more rapid technology transfer from what we develop to society by engaging private money. So this is the basic stuff, and making the way of engaging here private money is to make a profitable business, but which in any case is based on the technology, and technology must be kept being developed. So this is what the company does, is for the biomedical arena. It's basically for in-silico clinical trials. It is HPC cloud-based simulation, so this is deployed somewhere. Could be Mare Nostrum or somewhere else. It can be accessed through a interface, and we are focusing cell tissue and organ level. It is mostly organ level, but always take it into account the contribution of the different levels. Just to motivate you about what we do and why do you need a supercomputer, if you watch this TV show, it's a very nice one, Halt and Catch Fire. So in this TV show, one of the characters says this about that the important thing of these large computers, even they are very beautiful, very powerful. The operations team in BSc is kind of 40 people working to make this computer to work properly. But computers are nice, but what the important thing is the kind of things that you can do with the computer. So what you can do with the computer is the important thing, and this is what you can do with this large computer, and this is why we are there working on this. So the thing that we are trying to get is to, like this one, to try to recreate nature in the computer. So the more complex the system, the larger the computer. And the larger the computer, it is not just having the computer and installing installing Abacus for running using 5,000 cores. This is useless. What you need is also to make an efficient code to run in the computer. So this is our objective. The objective of the ALYA development team is to develop this very efficient code, and the objective of LM is to use this code, to put this code in the hands of biomedical stakeholders. So just a bit of the background. ALYA is our code, as I said before. It is used in industry-related projects mostly. We have several verticals like aerospace, energy, environment, and biomedical. These verticals are kind of our preferred verticals, those that were mostly developed all these in all these years. And related to today, I will talk about biomedical, which is the objective which is the underlying idea behind LM. It is important to say that this is good reason for doing these sort of things. It's the only multiphysics multi-scale code for biomedical use at organ level. That was born and developed in a supercomputing center. So if you go through this, you have a very stringent condition for running your code. You need to make it efficient, otherwise you're fired. So this was a very good motivation for. I mean, we did this code in this way because we had to. Otherwise, you go and work in other place. So the keywords of the code is that on the team. Typically, we use it for complex and conventional physical mathematical models that we can program in the code. Typically, meshing is large, which represents that post-process, which is visualization analysis, is very large too. Multi-scale, multi-physics problems, that's the kind of problems that we like. Again, the data management and visualization is difficult, so we need to think about ways of extracting data. And must be efficient and not just accurate, but also efficient for supercomputers. In order to write this wave, what we do is we think that all levels are accountable. So we have a large team, and also our team works in a very close connection with the computer science department and the operation department in BSc. In order to study all these different levels in which you can make your code more efficient. So it is like we attack every one of them of these levels. It is not just MPI, it is also the threads, and it is also the vectorization of the code and how you communicate between the different families, of course. Let's say then how to write and read large files, how to extract information. So it is a difficult problem. But well, the good point is that, as I said before, we have this direct interrelation with hardware manufacturers. We have early access to computers, and through the operations and computer science department, we can study how our code run in these different computers and what are the modifications that we must do. The code is very portable. It can run. It is running in different architectures and different supercomputers and architectures, as I said before. We work also with programming models developers. Well, many different things that thanks to work in a supercomputing center, we can have access to all these resources, which lead us to attack also and to study how to port the code to new architectures. One of our main premises is that we don't want to have many versions of the code, one that runs here, another one that runs there. So what we do is we try to have only one version, and this only one version, even if we lose a bit of efficiency. For instance, you can write all these subroutines with CUDA. Okay, but also you need other subroutines that are the same subroutines but written in C or Fortran or whatever. Our code is modern Fortran. So if or written in Fortran to run in another architecture, this is very bad because you need more. You need to duplicate the effort in order to keep these two subroutines, which are completely different, to maintain. It's more difficult. So what we try to do is always to have only one version. When when something that we can do, we can offload part of the code to run in GPUs. For instance, we have the solver can run in GPUs. I mean, we are always studying these sort of things in order to make the code more efficient. So far, no biomedical anything. So I've been talking about how to make the code efficient. Now let's use this efficiency and this power in the thing, which is the human body. And to me, it's the most complex and challenging problem, and it's very beautiful. By training, I'm a physicist, so I had no idea. Now I know a bit more, but not that much on anatomy, physiology, whatever. So just as a start, we started by kind of joking, and we group different verticals and their colors. So we use ALYA red, the red color, for anything that is because of the blood, for doing anything that is in ALYA, which is related to biomedical research. We started by focusing on cardiovascular in 2005. On cardiovascular, then we started to do other things on respiratory, and we did other things also in neuromodulation, bones. We did other things, but mostly today we are mostly focused on cardiovascular and respiratory. And thinking about the company, what we want is to put this in the hands of clinicians, but mostly to sell services to pharma and to medical devices companies. So these are, I will go through some of the examples, then you can, if we can discuss about the particular examples, but I think it's better to go just some examples and show you the kind of the capabilities of the things that it can be done. We follow this FDA vision about the things that has been done until very recently in order to follow a regulatory process for any medical device. For instance, there are plenty of laboratory human and animal tests and a bit of computer tests. And now what they say is that things are rapidly changing, and you have these human, animal, and laboratory tests that will be around. But what they want to do is to try to, in the regulatory process, reduce this by increasing computer and appearing a new character here, which is the virtual patient. So computer simulations are kind of things that are for experiments in vitro, and virtual patient would be modeling and simulation, now modeling and simulating the patient and everything that is related to digital health that is related to the patient, but included now in the regulatory process of a medical device. So we are more or less on this riding this wave, and we do things that are related to this computer and virtual patient, but especially with the virtual patient. So some examples of the things that we do on the cardiovascular system. I've been watching at the program of reading the program of this school, and it is very interesting because the thing that we do with our code can be, you can 90% of the talks of this school could be eventually done using our code. So it is kind of in the middle, and it is something that can be, we can say that it is kind of in common for the kind of problems that we solve. So it is it can be, it's a multi-scale multi-physics modeling of the cardiovascular system, so it can be around there in any of the talks that you have heard, in most of these talks. So we have a large amount of collaborators. Some of them became customers, but well, let's say by now that they are collaborators. This is a very nice quote taken from Streeter's book, The Handbook of Physiology, in 1979. It's very nice because if you read it, it's full of truth. And of course, it is already true. It's already true, and it is still true, and it will be true for years, many years. And it's it's very beautiful how it is posed and real. So to us, our virtual heart is like, from the engineering viewpoint, is something that you know and you have seen through many of these talks. You have you have one layer, which is the electrophysiology, and this is a description of what we have in our code. So in our code, we have these different cellular models that are linked to the diffusion equation on anisotropic media. That is the tissue that represents the tissue. Then we have this mechanics part and the electromechanical coupling between them. We have different tissue models, mechanical tissue models, like the Holzapfel models, the typical Holzapfel model, but we have simpler ones like Guccione, for instance. For the coupling, we have implemented one that was implemented by Francesc Lebrero from Oxford in our code, working with them in collaboration, which is the land model. But also we use the Hunter-Niederer model to coupling with the electromechanical one, in the electromechanical coupling. And then we couple these to blood with the fluid-solid interaction. So blood is solved, everything is solved in the same code, and blood is solved at this moment with Navier-Stokes incompressible. Can be, in this case, it's Newtonian, but non-Newtonian model can be implemented too. Well, the coupling between the different layers is related to the electromechanical coupling is a problem in itself, because it can be not controversial, but there are many versions, and there is plenty of physiology in it. The coupling between mechanics and blood is not that, it's complex from the computational point of view, but it is something that it is done, and there is no I mean, it has some computational problems, but it is okay, no problem with that. So that's the engineering point of view. But if you talk if you are talking with engineers, you say, well, but as a start, the main difference is with the aerospace is that, as we like to say, is that nature is not a CAD user. So you cannot have the CAD of your heart. You have to make it real from images. So the anatomy and physiology part of the problem of the scenario is difficult to get. Then the analysis of the results is difficult, and of course validation and verification. You're going to talk about this during this. It's also very, very difficult. And then mostly this validation and verification is related to a context of use and the quantity of interest that you want to use. So which is, what do you want? So this is the main difference with the general engineering viewpoint of a problem. So we achieve at the point that you say, okay, which is our first product? It's an in-silico clinical trials with a comprehensive computational model of the heart, which is deployed in supercomputers in the cloud. So let's just give a hint of validation and verification of the different points that are there at this there. So we follow this pathway for doing validation and verification. So it's one after the other. So first of all, you perform the scientific verification and scientific validation, which is something that you do continuously. You develop your code, and at the same time you have some selected problems. You're checking problems which have already run by others, and with that you can check that your code is doing more or less properly. Typically, there are simple problems. In the first case, extremely important is convergence analysis in time and space. Scientific validation is done from literature. In general, simple cases, mostly single physics. Then it is like there is a why, and you open in two different sides. One side is experimental validation, and the other side is the clinical validation. So the experimental validation is when you have, for instance, you will see later an example. So experimental validation is when you are doing something that is in vitro. So you have an in vitro example, something that we are doing now, in vitro example of an LVAD, which is this pump that it is used with patients that are about to have heart transplant, or for valve mechanics, in which you want to study bioprosthetic valves. So there you can have so you have an ad hoc benchtop experiment that it is done. So you can follow a validation protocol based on ASME. You can propose it, and you can do it. And the best outcome of this is the one certification. For instance, the MDDT. MDDT means Medical Device Development Tool. Then on the other hand, you have the clinical validation, in which what you want to do is to do something that is in vivo and based on measurements that are taken from patients. So in this case, it's very different because you have much lower control. The problem is going to be multiphysics. Maybe not, but maybe very likely yes. In fact, we like these multiphysics problems. And the best outcome would be a paper with a clinical validation. These are not done in continuum way. These are typically campaigns. So you find someone that can do the experiments, and you work with them, and you work with a hospital in which you have some retrospective data or prospective data, and you do this campaign. And always here you have context of use. So you are looking for some biomarkers. You are not going to compare in a general way, like in the previous one. You're going to compare with some specific biomarkers in both of the cases. Then you have here talks about generating synthetic patients databases like virtual patient. This is what we do. In this case, we are doing with the Visible Heart Lab in the University of Minnesota, and with this database that they have, you can create a virtual patient database. This is something in which we are working at this moment, in trying to extract the important information from. We have 40 explanted high-resolution hearts of different patients, extract information and trying to create a continuum change between different, to create patients, but with physiological meaning, not just hazard changes, something that it is. Well, it's plenty of work, and we are working on that. And then the multiphysics modeling. So these are some examples of what we have. So now the movie that you are seeing is is a multiphysics coupling. So here the atria is there just for give some mechanical support, but it is more on the, well, they're not just for mechanical support. So this is just a systole. Valves are fully open and fully closed, so there are no valves operating here. And what is systole, and it is colored by electrical activity. And it is contracting the heart, and the heart is pumping the blood. Then we disease, let's say, this heart by producing a left bundle branch block, and we add here a pacemaker. And we fine-tune the pacemaker in order to get to improve the cardiac function. This is another example. This is from one of our collaborators that asked us to do this thing with there is a pacemaker which is called Micra, which is a very small thing that goes pinned inside your right ventricle. So they wanted to see what are the kind of perturbations that this thing can produce in the blood flow inside the ventricles, which are the forces that are acting in the pacemaker, and because you don't want this pacemaker to get loose inside your body. So these are some, and of course, where do they have to put this pacemaker in order to make it better, working better? So this is one of these examples here. It is colored by something that it is very interesting to study is the Q criteria, which gives you an idea of where are the vortices developed in the fluid mechanics, which in turn, if you think about for the flow. You can compute these sort of things. So it could be a nice computational biomarker to study. This is another example. In this case is for some cardiac risk of arrhythmia. It was done with azithromycin and chloroquine drugs. So for this, we need as an input PK/PD of these drugs, and using one of the models that the O'Hara model, we can modulate the effect of the drug. This is done by Jasmine Aguado, which work the expert, but we are also working with the Oxford people. So to the right, you have the dosage that produces left bundle branch block. So it's not that good. These are some bioprosthetic aortic valves that we are working on now. In this case, the idea is to compare with experiments, with an in vitro experiment to validate the code. So you see in this case, these two examples. This is one with the much softer tissue, and the other one which is to the right, and to the left, something that it is much closer to reality, a rigid, a more rigid material. So the idea is to study here by the Q criteria how the fluid mechanics develop once the valve is open. So in this case, what we are doing is immersed boundary method on ALE ALE problems, because we want to put this inside the heart, and the heart is the mesh, the fluid mechanics problem of the heart is solved using ALE. So this is immersed boundary method on ALE, and doing anisotropic mesh refinement in order to get a better, well, a more efficient code. As I have no time. Yeah.
Are you reaching the end?
Yes, I will skip this respiratory system. Then we can talk about it. But okay, so all right. So the message that we want to deliver when someone well, okay, so you have in the audience there are people that are saying, well, but can a company do these sort of things? So the idea is that what the message that we want to deliver always is that, well, first of all, high performance computing is not needed everywhere in the biomedical realm. No, that's for sure. No. But for some problems, it is the only way. So that's where we are. We would like to focus in these problems in which using HPC is the only way. Now, HPC is mature enough to be used. It is not, it's not science fiction. You have algorithm solution schemes, implementation strategies that can be done. You can see us, we can do it. And we are not the only ones. There are plenty of people working on that, on the models. You can use these load balancing techniques in order to make to make your code more efficient. You have these programming models, hardware, software, hardware availability. Now almost everyone can use these very large computers. Okay, you have to propose to use it through a project, but everyone almost can do this. So the idea is that this is not science fiction. It is something that it is happening now. Then you can say, but well, it's difficult to validate. Fine, okay, fine, right. But you can do it. Then you can, as you can run the cases, you can validate at a certain point, because validation is, you have to establish the bounds at which, until which point is validated or not. Of course, there is a lot to be done on increasing the confidence on these tools, and this is related to validation. But look at other fields now. So this is done also in aerospace, energy, climate, in many of them. Industry and government are to fuel the pace. These are the COVID-19 lessons. So, but more hands are needed in these sort of things. And yes, we are hiring on the clinical and that provides clinical and medical insight, mathematical modeling. It is not just artificial intelligence. There are more things around. And good point also is that you can, right now, you can make some pressure, some small pressure on hardware vendors in order to make their hardware more better and more adapted to what you are doing. So, well, this is more or less what I wanted to tell you. So, thank you.
Yes, thank you, Mariano, for this very interesting presentation. Are there any questions from our ESRs? Yes. Andrew, please go ahead.
Hi, thanks for the very interesting presentation, Mariano. I was wondering if I've seen some recent work where they're using deep learning to map, to learn from some of the physical simulators to map either flow, or in other cases, using deep learning for some of the ultrasound beamforming, where you kind of train a network to mimic the process that's being done by these physical simulators. Is that something that you guys have looked into at all?
Yes, absolutely. I had other slides in which I talk about this, because and especially with multi-scale simulation, this is a very good way of doing modeling and simulation driven by artificial intelligence. So it is something that we would like to, well, we are doing our first steps on that, and we are studying which are going to be our next, but we are open to discussion about this. I think it's absolutely necessary, yes. Especially because these sort of multi-scale things are very difficult to validate, to bring confidence in them. So artificial intelligence methods are really very, very important. Yeah.
Okay, thank you.
Blanca, please go ahead.
Mariano, hola.
Hola.
Very nice presentation. I wanted to ask you, when you talk to investors, what is it that they are most interested in?
Yeah, that's a great question, and to us it's very timely because I am talking to investors in the next hour and being done this in all these through all these weeks. A ver, that's very interesting because the first thing is that they don't have to see this as a science fiction. They can see that this is a wonderful technology piece, but they must see the business there. So see the business there means that you have to do something. They don't like consultancy at all. So they want a product, not consultancy, because consultancy, you can do it, fine, but you must kind of hire it. So the idea is that what you can say is what we do, is what you can say, look, I'm working for Medtronic. So the Medtronic want to solve this thing. So first of all, we need to go through a kind of short consultancy stage because we need to understand the problem that they want to solve. We need to implement it in the code. If it is not that difficult, we can do it, implement it in the code, and then we can create something for them to use this by themselves. This is the kind of pathway that they kind of like. But the first question is this scalable in the sense that what if you have 3 customers with different needs and you need, well, you said that the team at BSC 50. What if you need 70 people to do this? How long it will take? So you said, okay, but I will pick problems in which this is scalable. And then the next question is, yes, but when? When are you going to give this product to them? When are they going to use it? And when are they going to pay? So the first, for them, this is much more important than the clinical validation and the technical part. Because also when you talk to medical device companies and you say, well, if you are solving these very complex problems, the medical validation is something that it will come. And it will, if you more or less give me the bounds of confidence and more proof of confidence, of course, more and more, but it's not that important. This will come. But so the investors are not that impressed by that. What they're impressed by is that if you can rapidly achieve a point in which you can deliver, you can create this, make this a business. This is the thing that they are mostly interested in.
Thank you. Thanks.